We're going to discuss parametric curves in this lecture. A parametric curve is obviously a curve that depends upon a parameter. Now, a parameter is a very commonly used word. It's even more commonly abused. So let's be very clear what a parameter means. A parameter is a number that can take different values. Examples: time, pressure, temperature, population of fish in a pond, for example. But the important thing is that upon that parameter, there could depend several other quantities. So, for example, if you take a particle that's moving in 2 dimensions, its x and its y coordinates will depend upon time. So time is the proper parameter over there. In this lecture, we're also going to study curves which do not belong to a function as such. A function, you remember, gives you just one value for every one input. But sometimes you can have things that go in squiggly ways, and then that's not the graph of a function. So let's remind ourselves what a function is. At the very outset, here's a quick reminder about functions. We've understood a function to be like a machine which, when given an input, produces an output. That input is in the form of a number x. What comes out is a number f of x, and we're free to call it y if we like. But this y has to be just one number for one x. In other words, it's got to be unique. If x is 1.3, y can be 3.9, and it can be nothing other than 3.9. Let me put it another way. Suppose that this is an interval with a and b at the ends, and there's a function that maps any number x which is within this interval. That interval is then mapped into another interval which we call the range, and let's say this is the number p and the number q. The number x is mapped to some number which lies between p and q, and the thing that takes it from x into this range is the function f. Now, if there's a different point x, let's say here, then the function f could take it, let's say, to here. But the point is that the same number x could not be mapped anywhere else into the range between p and q. Equivalently, we could say that if this is f of x, let's call it y, then y can be mapped back into x through the inverse function. So f inverse y, that's equal to x. Let me now try and say the same thing, but this time with pictures. Let's say that this is the point x equals a, this is the point x equals b, and this is, of course, the x-axis in this direction. The y-axis is here, and we've plotted a function y equals f of x, and that plot looks like this. Now, this is perfectly fine because for each value of x, there is one and only one value of y. So no matter where you are along this curve, the value of x fixes the value of y, and the value of y fixes the value of x. On the other hand, suppose we had a curve that looked like this. Now that's very different. Let's say that we look at this point along the x-axis and ask, what is the value of y? It could be this, or it could be this, or it could be this. In other words, the value of x does not fix the value of y. And this over here is not a function. So then the question is, how does one deal with such curves? The best way to think about this is to think of a particle. Let's say that the particle starts off over here at x equal to a, and it starts moving off with time. So now it is here, later it is there, then it starts coming back in x and wanders all over the place and ends up finally over here at b. Every point on this curve is, of course, fixed by a value of x and y, but now x is a function of time and y is a function of time as well. So as time goes on, x changes and y changes, and it changes such that the point or the body remains on this curve. This t is called a parameter. And it doesn't necessarily have to be time. It could be anything else. But let's, for convenience, think of it as time. So the particle is moving along this path. If you, let's say, start at t equal to 0 seconds and it reaches its destination at t equal to 1 second, then at t equal to, let's say, 0.3 seconds, it will be somewhere on this curve. Where will it be? That's determined by the function x of t and the function y of t. Another way of saying this is that every point on a parametric curve, and so this over here is what is called a parametric curve because it is parameterized by t. So every point is of the form x and y, where x is a function of t, y is a function of t, and the values of t are specified to lie within some interval. In this particular case, that interval of t was between 0 and 1. As our first example, we're going to take a curve that's parameterized by t, where t lies between 0 and 2 pi. X is cosine of t, y is sine of t. And I've made a little table over here, not a very big one, but for different values of t, I've calculated x and y. Now let's plot out these points on the usual x and y axes. You see that point number 1 is here, point number 4 is there, and so forth. Now I'm going to ask my computer to start drawing a graph. You can see at the bottom that t is taking different values. It started out from 0 and went up to 2 pi, but now it is decreasing. It's going back towards 0. The points x and y clearly lie upon a circle, and that circle has radius 1. Of course, it's completely trivial to see that this is the equation of a circle, because if I take x squared plus y squared, that's just cos squared t plus sine squared t. And you know from trigonometry that that is equal to 1. And that's the equation of a circle with radius 1. This second example is going to be very similar to the first one. The only difference is that x will now be 2 times cosine of t. Y will remain sine of t. The interval is the same as before. And again, we make a table. When t is 0, x is now 2, y is 0, etc. And then as t changes and reaches 2 pi, we come back to the original point. Well, now let's take the coordinates and put them as points on this graph over here. So here is the point t equals 0. That'll be the first point. And now I'm going to ask the computer to change t. As t increases from 0, comes to pi by 2, then to pi, then to 3 pi by 2, and then finally to 2 pi, an ellipse is completed. Its width is 4 units, its height is 2 units. By the way, an ellipse is the path that the planets follow around the sun, and this is what you will learn in classical mechanics. Now let's see if we can understand this curve analytically. So let us eliminate t from this equation and this equation, which is easily done because if I take x squared over 4 plus y squared, that's cosine squared t plus sine squared t, which is 1. And so we have y squared is 1 minus x squared over 4. This has, of course, two solutions. Y can be either plus square root of 1 minus x squared over 4, or y can be minus square root of 1 minus x squared over 4. Now, these are actually two different functions, and I haven't done well by writing the same symbol over here. Actually, I should write y1 and y2. You can immediately see that when x is 0, y will have two possible values. It can be either plus 1 or it can be minus 1. So it can be here or it can be here. So this is clearly not a function. And of course, we could have done the following, that put y equal to 0 and then x would be plus or minus 2. So either here or over here. By parameterizing this curve, we've actually plotted something that is not a function. As a third example, let's plot the curve x is t plus 1 over t, y is t minus 1 over t. And we shall do this for all values of t which are bigger than 1. As you'll see just a little bit later, t equals 1 has a very special significance. So here is a little table over here. When t is 1, then obviously x is 2, y is 1 minus 1, which is 0. And here t is allowed to take values 1.5, 2, 3, 3.5. When plotted out, these give the blue dots that you see. And now let me increase the value of t from 1 upwards. So you can see that I'm increasing t, and this is plotting out a curve that looks like half a hyperbola. Now let's try and understand this curve analytically. As a first step, we shall eliminate t between the two equations that you see at the top. So if we add the two equations, x plus y becomes 2t, and x minus y becomes 2 over t. That immediately gives t is 2 over x minus y. And when I put this value of t into the other equation over there, then I get x plus y is 4 over x minus y, which immediately gives x squared minus y squared equals 4. There are many ways to understand this equation. Well, first of all, let's write this as y squared equals x squared minus 4, which then gives two solutions for y. So y can be either the positive root plus square root of x squared minus 4, or y can be the negative root minus square root of x squared minus 4. Now, if we look at this equation, we see that this gives a relation between x and y for all values of x. Here, on the other hand, we're only looking at positive values of x between 2 and infinity. So we haven't got the complete curve as yet. To be more specific,
So far we've looked in this region, t between infinity and 1. That's the condition that we were given over here. T has to be greater than 1. But there are 3 other regions. So t can be less than 1 and still be positive. Then t can be negative but greater than -1. And finally, t can be less than -1 and greater than -infinity. So there are these 4 regions of which we have plotted only this region over here. As an exercise, I'd suggest that you plot the remaining 3 regions as well, and that will tell you that this graph that we've plotted up over here will actually look something like this. So it's going to look like this on that side and like this on this side. But that's an exercise for you to do.
As our 4th example, let's plot x equals cosine cube t and y equals sine cube t in the range of t between 0 and 2 pi. This is actually going to lead to a rather pretty figure. When these are plotted out on the x and y axes, you can see that these points are distributed in a very nice symmetrical way. Now when we connect them up, they make a very pretty figure indeed, and this is called an asteroid. That's not to be confused with an asteroid. The asteroid has got 4 cusps and it is a very symmetrical figure. It is the same whether it is reflected along the x-axis or along the y-axis. I'm now going to talk about a very famous parameterized curve called the cycloid. This motorcycle, which is moving at constant speed, has picked up something on its wheel, and as the wheel goes around, it goes up and comes down. The wheel is moving without slipping, and the motorcycle is moving at constant speed. The center C, which you see before you, is therefore moving at a constant velocity. On the other hand, the point P, which is on the rim, goes up and it comes down. Let's now look carefully at the motion of this object that's gotten stuck onto the wheel. This is the point P. Its coordinates are x and y. The radius of the wheel is 1. So the height of C above D is 1. And this point, which is the red point here, goes all around as the wheel moves to the right. This angle here is t. When t is 2 pi, this point will have moved a distance 2 pi. Now let's look at this distance here. Obviously this is sine t, and this here is cosine t. So x is going to be the distance d, which is t itself, minus sine t, and y will be the height of the point P above the ground, which is 1 minus cosine t. These are the parametric equations of the cycloid. Like with the other parametric curves, we'll plot out this cycloid too. X is t minus sine t, y is 1 minus cosine t, and I've made the table as usual. Here are the points plotted out between 0 and 2 pi. If I want to go beyond 2 pi, then obviously the pattern is going to repeat itself. Now the computer is plotting out the cycloid, and you can see that it is indeed repeating itself and will keep repeating itself. Of course, we can allow t to go backwards, in which case that wheel is moving in the other direction, and it will then keep going. Now that we've plotted a number of parameterized curves and seen how different they are, we can ask, how do you calculate the slope dy by dx? Here, let's remember that x is a function of t, y is a function of t, and y certainly depends upon t, but it depends upon t through x. So y is a function of x is a function of t. Therefore, by the chain rule, dy by dt is dy by dx into dx by dt. And from here, dy by dx is dy by dt divided by dx by dt. And that's how you calculate the derivative or the slope of a parameterized curve. We can use the formula that we just derived for finding the value of dy by dx for this hyperbola. As a first step, let's take dx by dt. Well, that's 1 minus 1 over t squared. And similarly, dy by dt, that's 1 plus 1 over t squared. And so obviously dy by dx, which is the ratio of the two, is 1 plus 1 over t squared divided by 1 minus 1 over t squared. And that gives us t squared plus 1 divided by t squared minus 1. Well, let's check to see if we are doing the right thing. As t tends to 1 from above, obviously we are restricting ourselves to t greater than 1, then dy by dx, according to the formula that we just derived over here, t squared minus 1 tends to 0, so dy by dx tends to infinity. So that means that when t is 1, or equivalently we are at this point, the derivative becomes infinite. And so you can see, in fact, that's exactly what's happening. The derivative has become infinite at this point over here. What happens as t becomes larger and larger? In that case, we can see that dy by dx tends to 1. And equivalently, you could see from this formula over here that x would tend to t and y would tend to t also, because 1 over t gets negligible. So y tends to x. That's telling us that the slope at infinity, that is to say this gets closer and closer to 1. So the slope becomes closer and closer to 1 as t becomes larger and larger. As a second example, let's calculate the slope for the asteroid with x equals cosine cube t, y equals sine cube t. And remember that this over here is the point t equals 0. This is the point t equals pi by 2, and so forth. Now, take dy by dt. This is 3 sine squared t into cosine t, and dx by dt will be the same thing almost, but with a negative sign, and we'll have cos squared t sine t. So dy by dx, which is the first divided by the second, so that's 3 sine squared t cosine t divided by minus 3 cosine squared t sine t, that is just minus sine t over cosine t, which is minus tangent of t. Okay, now let's see what happens as t becomes small, in which case dy by dx tends to 0 as well. And so the curve is flat over here near t equals 0. And now let's see what happens as t tends to pi by 2 from this side. So as we go from here, you see that dy by dx is approaching minus tan pi by 2, which is minus infinity. And so at this point, the derivative goes to minus infinity. You can see it's very sharply sloping upwards. Next, let's let t tend to pi by 2, but now from this side. So dy by dx here tends to minus tan pi by 2, but approach from the other side, that's plus infinity. So you can see that the derivative does not exist at this point. It also doesn't exist at this point. Here you can see that the derivative is positive towards the right, and here the derivative is negative towards the left. I'm now going to derive a formula for the length of a parameterized curve. So let's say that we start from this point over here, and we walk along a path that goes up and down, maybe goes back upon itself, and ends up over here. If we look at a small portion of the path, so here is one point, here's another point that's close to it. It took delta t time to go from here to here. We could have walked delta x in the x direction, delta y in the y direction, and for delta L, that makes delta L squared equal to delta x squared plus delta y squared. Now, let's write this slightly differently. Let's write delta L as the square root of delta x squared plus delta y squared. And now let me divide this by delta t squared and this by delta t squared and multiply by delta t out over here. So as delta t becomes smaller and smaller, this will go over into dx by dt squared plus dy by dt squared dt. If we break up our path into several straight line paths, and here for illustrative purposes I've just drawn 5 of them, this, and this, then the total distance that we have traveled is the sum of these distances, and hence the total distance will be the sum of all these little distances, and then this goes over into the integral of square root of dx by dt squared plus dy by dt squared. What are the limits? The starting time, let's call that t starting till t finishing. Those will be the limits of the parameter t, and they will give us the total distance that we will have walked. As our first example, we're going to treat a rather easy problem, which is that of a part of a circle. If we start from t equals 0 and end at t equal to 3 pi by 4, we can actually guess what the answer would be, but let's use the formula that we've derived up over here. So if x is cosine t, dx by dt is minus sine t, and dy by dt is obviously cosine t, And so S is then the integral dt 0 to the maximum value of t, which is 3 pi by 4. We take the square root of dx by dt squared, which is sine squared t, and then the square root, and then dy by dt squared, which is cosine squared t. And of course, sine squared t plus cosine squared t is 1. So this is just the integral of 1 from 0 to 3 pi by 4, and that is 3 pi by 4. If instead we had completed the circle, gone around on a complete loop and ended up at t equal to 2 pi, then the distance we would have covered would be 2 pi. And that, of course, is the circumference of the circle. The second example is a little more challenging. We are asked what is the total distance we will have walked if we start over here at t equals 0, walk along the path, come to t equals pi by 2, then walk until we reach here where t is pi, keep walking until we reach t equals 3 pi by 2, and finally we end up at the same point that we started from, which is t equals 2 pi. Now, what we need to do is, first of all, calculate what's inside the square root sign, which is dx by dt squared plus dy by dt squared. And obviously, when we differentiate x with respect to t, we're going to get 3 cos squared t, and then a minus sine t squared, and then 3 sine squared t cosine of t squared. This works out to 9 cos to the 4t sine squared t plus 9 sine to the 4t cos squared t. And we can clearly take 9 cos squared t sine squared t common, and inside is cos squared t plus sine squared t. And since this is 1, we've found that this is just 9 cos squared t sine squared t. Now, if we take the square root of this, we get 3 cosine of t sine of t. And so what we seem to have is this, integral t from 0 to 2 pi, and here we have 3 cosine of t sine of t. But cosine of t, sine of t, is just half of sine 2t. And so this looks like 3 over 2 integral 0 to 2 pi sine 2t. But when we integrate sine 2t, see what we get. We get half cosine 2t with a minus sign between 0 and 2 pi. But the values up over here at the upper limit and at the lower limit are exactly the same. And so this gives 0. Now that doesn't make sense, does it? Because after all, we've walked around this curve, and surely we must have covered a distance, and yet this formula is saying that s is 0. So is the formula wrong? The answer is no. It's just that we need to recognize that distance is always positive, but sine 2t keeps changing its sign. However, now let's ask, what is the distance that would be covered if we go from 0 till pi by 2? In other words, starting from here and ending over here. Now, if we just put this over here, 3 over 2 sine 2t, and this is now minus 3 over 4 cosine of 2t from 0 not to 2 pi but to pi by 2. This answer, of course, is plus 3 by 2. So we have covered a distance 3 by 2 in walking from here to here, and the total distance s will be 4 times 3 by 2, which is 6 units. So that's the correct answer. Only the positive sign of this square root ought to be taken. So basically we have split up the integral between 0 and 2 pi into this part, this part, this part, and this part. And hence the answer is 4 times 3 over 2. The cycloid is such an interesting curve that really we must ask, what is the length that we will have traveled if we walk along this cycloid starting at t equals 0 and ending at t equals 2 pi? Well, let's calculate dx by dt squared plus dy by dt squared again. And obviously, if I differentiate x with respect to t, I'm going to get 1 minus cosine of t squared. And if I differentiate y, then I'm going to get sine of t squared. Let's just open this out. So this is 1 minus 2 cosine t plus cos squared t plus sine squared t. But cos squared t plus sine squared t is 1. So therefore this is 2 into 1 minus cosine of t. On the other hand, I can write cosine of t as 1 minus 2 sine squared t by 2. So this is 4 sine squared t by 2. Once I take its square root, then what I need to do is calculate the length dt of 2 sine t by 2. Now let's see when sine t by 2 is positive. When t goes from 0 all the way up till 2 pi, then indeed this is always positive. So we can go from 0 to 2 pi. There's no problem over that. Integral of 2 sine t by 2 is 2 into cosine of t by 2 with, of course, a minus sign. And this goes between 0 and 2 pi. So this gives us 8. That's the length that we will have walked in going from 0 to 2 pi. At the outset of this lecture, I said there were many different kinds of parameters that were possible. Here we focused upon just one, time. In the next lecture, we're going to discuss polar coordinates, and there'll be a parameter. That parameter will be the angle theta. And again, we'll be able to see very nice, interesting curves that depend upon the parameter theta.